Good morning from New York City. Some people ask me to do some solid state stuff. I'm doing the density of states. It's a fundamental object, not only in solid state physics, but in many aspects of physics. And the density of states is much deeper than people think. This is preliminary. I'm going to do this talk in a different way than I've done previous ones. Usually I go straight through for a half an hour and derive everything live. Sometimes I make a mistake and then I have to do a correction in the next class, because that's what happens when you do things live. Now, I'm quite capable of doing this live too, but I'm going to try a different tack because I figured out something. In the past, my lectures were 1/2 hour, maybe 40 minutes, straight through with no break. I figured out how to splice videos. So I'm going to do this one in stages. So the density of states. Okay. First of all, I'll give you some preliminaries. I will define density of states. That's part 1. Then I will stop, erase the board and do part 2. Then I will look at a model for a metal. It will actually be a particle in a box, and we will solve the Schrödinger equation for a particle inside a box of size L. I'm making it a cubic box just to make the calculation easier. The density of states is independent of shape. So it doesn't matter what shape the box is. Could be a triangular box, anything. The density of states is independent of shape and volume, of course. Now the next thing, after the particle in the box solving the Schrödinger equation for the particle in the box, I will come along and derive the density of states formula by at least one method. I have about 4 or 5 actually, but I have a simple one that will be very transparent for you guys. First of all, let's do the preliminaries that I've organized here. Okay, as I said, the density of states is unique and volume and shape independent. It could be a fundamental object. It could be more fundamental than some of us realize. This lecture, from beginning to end, as usual, is theory. When you see AK lectures, for example, he does a very good job, but he doesn't derive much or anything. He quotes equations. I basically derive all equations and don't quote much. I don't go into too much talk in terms of physics. My attitude is the less talk you do, the better. The equations will speak for themselves. Now the symbol for density of states in terms of energy will be rho of E. In K space, rho of K. P is H cross K. And we could work in number space. You don't know what this is yet, but it's going to be like this. There are going to be discrete solutions to the Schrödinger equation for a particle in a box, harmonics if you like, and this n numbers the harmonics. In a 3-dimensional box, this will have 3 components. So will this, and so will this, okay? Now what is density? Density, first of all, go back to high school or middle school chemistry. Density is mass per unit volume. Mass, kilograms, unit volume, cubic meters. How many kilograms is a cubic meter of water, for example? I can tell you off the top of my head. Actually, I'd have to work it out. I think it's 1,000. 1,000 grams. Anyway, for water, the density of water is 1 gram per cubic centimeter in grams per cubic centimeter. I remember that much. So, grams per cubic centimeter are mass density units, and it's the same throughout. But the density may change. So if we solve for mass is going to be rho times V. Density times volume. Now, if the situation is such that this is R dependent, this rho is a dependent of R, let's say, varies throughout the object, we have to integrate over the volume that's involved. And such a function like this is generally known as a density function. Now, go back to quantum mechanics. Remember what the density function is. Mod psi squared. Square interval solution to the Schrödinger equation is required for it to be a valid solution. And of course, if a particle is in a box, it must be in there somewhere. We integrate over the whole region where that particle is. Mod psi squared must be equal to 1. Okay. Now, I use this symbol here. If you see a squiggle under here, it's really deep 3x. It's a vector, and you can transform to scalar. We'll talk about this in a minute. Now, the next thing to do is, what is an expectation value? An expectation value works like this. Actually, I'll leave that for a separate talk. I have a great talk on expectation value, but the expectation value of a physical observable, call it O, is found by putting the physical observable in between psi and psi bar and operating on one of the psi bars and integrating over all space. Okay, now let's go and define what we're going to need. What is the density of states by definition? I will do it this way. Rho of E is the number of solutions to the Schrodinger equation per joule per cubic meter. All right? The number of solutions is another way of saying the number of states. The number of solutions of the Schrodinger equation, in our case, it's going to be in a box, a cubic box, and the number of solutions per joule of energy per cubic meter. Right? So that's density of states. We can write it like this. Rho of E is 1 over V, where V is volume, dN by dE. Okay? Number per unit, energy per cubic meter. That's the same as this. Now, when we do our calculation of the density of states, we're going to check the dimensionality of our answer to make sure that we're on the right track. Dimensional analysis will allow you to get a formula up to a constant. dN is going to be the number of solutions between K and K plus dk, or E and E plus dE. We'll talk about that in a minute, or N and N plus dN, and that really defines, not a disk, what's the word for that? Kind of a disk. We'll come to that in a minute. So we can go in K space, N space, or E space. Real space is the usual X, Y, Z. That's a separate idea. The box is in real space, and it's going to have a volume L cubed. We're going to talk about that in a minute. I'm going to erase the board, and we'll get on to solving the Schrodinger equation in the box and get our working result, because it will serve as a model for a metal. In a metal, electrons are tightly bound. They will stay in the metal and not leave it unless you get a photoelectric kind of effect coming in. Let's say you hit it with gamma rays or X-rays, then the electrons will be thrown away. But without doing that, the electrons are tightly bound in the box. So, we will have a box whereby the potential is 0 inside and infinite outside, so that the electrons are stuck in there. That makes a good model for electrons. The electron C, some people call it. Okay, so let's leave that until we go solve the Schrodinger equation for the actual particle in the box, which will be our model for a metal. Taking a break now and erase the board. Good morning. I'm going to continue with the analysis of density of states. Part 3 will be the derivation of the result for the density of states itself. This is the lead up to it. Now basically what we have here is we have a box of size L. Cubic box, L cubed is the volume. Centered on the origin here with one corner. L in the X direction, L in the Y, L in the Z. And it's a standard problem. The box models an electron with tightly bound electrons moving in an electron C. The electrons do not leave the box. The electrons do not leave a metal either, right? Unless you use the photoelectric effect to eject one. The potential is 0 inside the box and infinite outside the box. This is potential. This is volume. Volume is L cubed. So, what's the Schrodinger equation for this situation? Okay, here's the Schrodinger equation. Minus h cross squared over 2m, d squared by dx squared, d squared by dy squared, d squared by dz squared. We call this nabla squared. Not del, nabla squared. It's a Greek letter. Now we have boundary conditions. In the x direction, psi x plus L equals psi of x. Similarly, that's the sign for similarly, for y and z. I don't have to keep reproducing the situation for y and z. And let's do the same thing over here because it's exactly the same in the x, y, and z direction. It's uniform in each direction. Okay, so del squared psi plus, now, 2me over h cross squared. We will designate that to be k squared. K squared is 2me over h cross squared. K squared. We'll make it 2me over h cross squared. And just for convenience, I'll solve for k, the square root of that, 2me over h cross squared. And e, I'll solve for e, h cross squared, k squared over 2m, which is p squared over 2m, as usual, because p is h cross k. Now we use the separation of variables. Let x equal phi x of x, phi y of y, phi z of z. Separation of variables means we substitute this result in, and this k squared is the magnitude of a vector, kx squared plus ky squared plus kz squared. In the usual way, when we divide across the whole equation by the product, phi x, phi y, phi z, divide across, we get three equations that look like this. That is the simple harmonic motion equation. D squared phi, not quite, but d squared phi by dx squared, it looks like it, plus k squared phi equals 0. Okay? Now the same result is true for phi y of y, phi z of z, and the solution, phi x of x equals a sine kx of x plus b cos kx of y. Because of the boundary conditions, we require that the solution is 0 at x equals 0 and x equals L. That boundary condition designates b to be 0, so that just the solution a sine kx of x exists. Our next job now is to write the full solution and find out what the a is, right? We have to find out what this constant is, and we use the normalization condition. Let me clean the board and do that. I don't want to waste time cleaning the board. So we write out our full solution here now. Where is it? Here. Phi x of x. Using the three solutions for the x direction, we go psi of x, y, z. We'll call this a dash. It's actually going to be a cubed. We'll call it a cubed because need this. So that is going to be our solution in the end, but it's going to be the product of three solutions that look like this. So we just now analyze phi x of x. Now the solution requires on the boundaries that this is 0, so therefore then KL in the x direction equals any number of pi's. N pi or pi n, call it what you want, because an integral number of pi for sine means it's 0. Sine looks like this. 1 pi. 2 pi's, 0 at each point, okay? So KL is n pi, so therefore then Kx is going to be nx pi over L. in the x direction. Now we normalize this to get what A is. The wave function normalized to unity just states that the electron has to be somewhere between x equals 0 and L, and similarly in the y directions. So that's going to be sine squared n pi x over L. And using the trig identity, sine squared equals 1/2 times 1 minus cos 2 theta, we'll substitute in for that and carry out the integral. Now the integral of the first part is easy enough. That's for the first part. And for this part here, now I should have an x in there somewhere. X, 2n pi x. Well, when we set x equals 0, this is going to be 0. When we set x equal L, 2n pi, L cancels with L when L is x, and that's also 0. So this whole term is 0. So all we get is x over 2 from 0 to L, which is L over 2. Okay? Now 1 over a squared is L over 2. So therefore then A is the square root of 2 over L. So now we have our full solution. I'll let you get your heads around that. Full solution is the same in the y direction and the z direction, and our A is going to be the same because the thing is uniform in each direction. So I'm getting our full solution now to be A this should be a Z in here over L. Sorry, I didn't have enough room. To the power of 3 over 2. That's going to be 8 over L cubed to the power of a half and we have to distinguish these ends. They're different in each direction, so we label that nx, this is ny, and this is nz. And now we have to look at the structure of this solution when operated on with nabla, and we're going to find that there's interesting behavior in this solution, and I'll deal with that now. I'll clean the whole board, and I'll just take a two-minute break to clean the board and come back and continue with this. Okay, so we're continuing with the density of states. In a minute I'll actually derive the density of states in the final form. I will do a quick version of that too, separate from all of this build-up, because people will get confused with the build-up. All we're doing is solving for a particle with in a box at first. I'll go over what we got already to remind you. We get psi x equals the product of phi of x, phi of y, phi of z. Three different functions with the same structure that are solutions to three separate equations resulting from these operators here acting on this combination in separation of variables. So if phi of x is one of the functions, the other two have the same structure, is a sine n pi x over L, with the n pi over L set in there to agree with the boundary conditions that the function phi of x is 0 when x equals 0, and also 0 when x equals L. So then we want to find out what the constant is. Well, we just normalize the function. Now that basically says that the electron must be somewhere, so that the probability amplitude of finding the electron between 0 and L has to be 1. 1. So we integrate from 0 to L over the function squared. Phi complex conjugate squared is what this is. Sine squared n pi x over L dx is the same as a half times 1 minus cos 2 n pi x over L. This integrates into a constant very quickly, x, and we work it out between 0 and L at the extremities. So 1 over a squared, we bring the a squared over here underneath the 1, is going to be x over L between the extremities 0 and L, which is simply L over 2. Now for this one here, we go from 0 to L, so 2 pi n pi x L over L is 2n pi, so that is a 0 quantity because n is an integer. And sine of 0 is also 0, so this whole thing is 0, so we're left with only with L over 2. 1 over a squared is L over 2, so therefore a is the square root of 2 over L. I'll let you get your hands around that and then I'll clean it. Okay? Now I'm doing this a slightly different way. Rather than deriving live, believe me, I'm quite capable of doing all of this live, just that I don't have my back to the camera so much when I do it this way, which is what I do when I'm deriving live. So therefore then we have psi of x. The constant here has to be cubed, I'm sorry. And that's our wave function. Now, let's operate on this. What we're saying here is L squared psi plus k squared psi equals 0. That's the Schrodinger equation, where k squared is 2me over h cross squared. Okay? Operating on this, d by dx psi of x gives me n pi over L times minus cosine x. D by dx minus cosine of L gets this to be squared, drags out another term, nx squared, and the pi over L to be squared. So I did it for x, y, and z. Taking the second derivative also brings in this minus sign, right? So then if I bring this all to the left-hand side, I get nx squared plus ny squared plus nz squared times pi squared over L squared equals k squared. And once again, k squared is 2me over h cross squared. We can write k as a vector, kx, ky, and kz, and its magnitude is k squared. Sometimes we write the magnitude like that. Magnitude of a vector is k squared. So now what have I got? Well, we can have n space and k space. Here's a vector in n space. Nx squared plus ny squared plus nz squared. So this implies that nx squared plus ny squared plus nz squared times pi squared over L squared equals K squared, which is kx squared plus ky squared plus kz squared. So now we can work either in n space or k space. Let's go into n space. Well, I have to bring this over to here. Now this defines a sphere, okay? This also defines a sphere. This is a sphere. Let's work in n space only. So, oh yeah, we want to get the energy eigenvalues. Before I erase this part of the board, this is going to be a sphere. We'll come back to that in a minute. So we have n squared pi squared over L squared is k squared, where k squared is 2me over h cross squared. Well, this is nx, ny subscript nz. These are the eigenvalues of energy. So the energy I can rewrite by solving for E. Where's the k squared? Okay, this thing here. So we get E nx ny nz is h cross squared over 2m n squared pi squared over L squared as being the energy eigenvalues. We'll use those later. I want to look at this sphere. So let me erase this part here now because we're finished with it. Get your heads around that. Okay. So let's look at, make this a bit clearer. I don't like the look of that. All the n's, nx, ny, and z are integers. And it's a sphere of radius r. So let's look at that. So we have in the x direction, y direction, and z direction. Now in this sphere, the maximum or most energetic electrons are at what's called the Fermi level. Right? K squared is 2me Fermi over h cross squared. This defines the most energetic electrons, the ones out here. Fermi energy we can solve. Is h cross squared kf squared over 2m. We can just keep rewriting this in different ways. Fermi momentum, Fermi energy, Fermi level, Fermi this, that, and the other. Now, if we look at all the points in this space, here's a point in the space. Here's another point. Here's another point. Another point. As you can see, these all isolated points are integrals of ny and nx, ny, and z. So they are dots in this space. Each dot occupies a particular space. Now what we're going to do is this. As you notice, there are no negative values. So therefore then we exclude all of the part of the sphere. These pens are not working very well. So when it comes to working out how many points there are in this Fermi sphere, what we do is we only take this octant here, the positive octant. Let's note that by red. It's an octant. It's 1/8 of a sphere. And it's in there. And it has all the points in it. Now there are a very large number of points here. So you can't be envisioning huge big gaps between the points. Let's see what the gap between any of these 2 points is. Well, in x, y, or z directions, k is n pi over L. This is the gap between 2 points in k space or L space, either one. So 2 neighboring points differ by only 1 space. N plus 1 minus NL gives me pi L. I'm going to call this pi L, L0. Pi over L. Okay? So let me get this off because you've seen the octant. This kind of phase space in K space or N space, we can operate between either one of them. I'll call this Rn. I could have Kn. Differing only by a constant. Sphere in K space or a sphere in N space. Okay. I also could have energy space. But we'll leave that complication out. So once again, we realize that there's a very large number of these discrete points occupying the octant, which is only positive, positive, positive. Now we're looking closely at the volume, first of all, let's say the area of a little cube occupied by 1 electron. 1 electron, 1 state. Now we can actually put 2 in there, but let's just deal with 1 first. What's the volume of this little cubelet? Well, it's going to be L0 cubed, this one. Let's just say the volume of 1 state is pi cubed over L cubed, and we'll call this V0. Now, if we want to find the density of states, we'll divide this into the whole space and find out how many of these things exist, and that will give me a total number of points in the space. That's separate for another part. That's coming up in a minute. This is all we want to get for now. That is that we have a sphere. Let's look at this sphere again. These are the space points. So r squared is going to be given by L squared over pi squared 2m E Fermi over h cross squared. This is the sphere of points. Let's look at k squared. Well, no, that's enough for that. Now we leave it. Okay then, let's move on in a minute now to the actual density of states itself. We've more or less set up all the background details. Next is a quick derivation. Coming up in a minute. Good morning from New York City. It's a bit chilly today. So, we're going to continue now with the longer version of the density of states, and I tend to already put the stuff on the board, but the very first time I did density of states, I derived the complete thing from beginning to end. I did not use notes. That's a shorter one. This one is a bit longer, and I put the notes on the board. It's not that I can't do it, it's just that I can turn around and talk about them rather than keeping my back to you. So, what we got already was for a cubic box, which is going to be the model for our metal. Now we put it into a cube because it's easy to calculate with the length equal to L, the length of each of the sides of the cube. For separation of variables, for this particular equation here, the Schroeder equation, where k squared is 2me over h cross squared, E is h cross k squared over 2m, or p squared over 2m is what we expect the energy to be. This is the equation of a sphere, okay? We can look at it in n space or k space. And don't forget, these n's can be only positive integers, 1, 2, 3 in the x, 1, 2, 3, 4 in the y, 1, 2, 3 in the z. So when we're calculating things, we look at only a positive octant. Positive octant. We want to calculate what? The number of states or points in this region, right? Okay. So we look at the cell in the region, the distance. Okay. Each kn is n pi over L. So the width between any two cells is just 1 pi over L. Pi over L is the cell width. So the volume of that cell width is going to be pi cubed over L cubed. And L is still the length of the sides of the box. Why can we use a cube? Because the density of states doesn't take care of what shape it is. And it doesn't care about the extent of the volume. So we can morph the cube into a hemisphere if we want. That's the volume of the box. We'll call that V0. So the total number of states in the box, oh, by the way, I'll use this vector, k squared is k dot k, which is kx squared plus ky squared plus kz squared. I can go into that's the radius of the sphere. It's going to be k squared, but I can look at it the other way around. We'll call this one r dash. If we're working in n space, that's the radius of its sphere. Doesn't matter which one you look at. So if we look at k space, the volume of a whole sphere is 4 over 3 pi k cubed. The volume of the octant is 1/8 of that. But there are 2 spin states per octant. One electron can have spin up and the other one spin down, so we double the number of states. The total number of states is this whole number divided by V0. V0 is just pi over L cubed. We can write that pi cubed, L cubed up here. Now, let's consider dn. What is dn? This is dn. This is n. This is going to be dn. It's a number of states between k and k plus dk in a shell around the octant. So we go, what's the number of states? Well, let's say what the width of the shell is. For the volume of the shell, 4 over 3 pi k plus dk cubed, the big shell, minus the volume of the little shell, 4 pi k cubed, and the number of states in that we divide by V0. So big volume minus little volume over V0 will give me dn. Work out that. Cube the k plus d cubed and you get k cubed plus 3k squared dk plus 3k dk squared plus dk cubed. And don't forget we have to take away this one as well. Now 3k squared to k is all that's left, and that 3 cancels with that 3. K cubed cancels with this k cubed. Dk squared goes away because dk is very small. Dk cubed is really small, so it goes away too. So that the volume of the region is 4 pi k squared dk, and the number of states in that region we find by dividing by v0. And then we have to change to E to calculate the actual density of states. So let me erase the board. Now it's still wet. Now we want to put in for dn. Well, that's what that is. Now v0 Now L cubed is the volume of the box, so I could change the L cubed down here and put the pi cubed in and bring it up here. So dn now k squared, remember what that was. So I put in for that. And dk is the variation of that. 2me over h cross squared, take the variation of it. Okay? Variation of this. Now the e to the power of a half. It's the derivative of e to the power of a half and dE. So I put in for that. This goes in here. Sorry. And so that's what I get, okay? This is to a half. Now let me check on that. Yeah, it's okay. So now, e to the power of a half into this goes e to the power of a half up here. To e to the power of a half. Now, if I missed anything. Okay, so I can combine these two guys at least, and there's to the power of a half in there. Combine this one here. The power of 1 plus a half is the power of 3 over 2. E to the power of a half. dE. Okay, so now I go for the density of states. We'll put it up here. That's dn. Now I need dn 1 over v dn by dE. Now I'm missing a v here. The volume of this space I forgot to carry down. It's got to be here. So if I divide out the v, this guy goes away. And I divide out the dE, this guy goes away to get this expression. And that's the density of states. Now what's coming up next is applications of this. Okay? Very good. And there's lots more to come.